Assalamualaikum and greeting. My name is Aisyah Binti Anuar. I will present about the proposal final year project 1. My supervisor is Dr. Muhammad Haikal bin Abdul Aziz. My first co-supervisor is TS Dr. Nurhanis Hayati binti Khairul, and my second co-supervisor is Dr. Nur Faiza Razali. My final year project title is Super-HYDROPHILIC and in water super-oleophobic kaolin modified polysulfone PSF microfiltration membrane for oily water purification. I will explain about the presentation outline. The first one is the introduction, which I will explain about the research background, problem statement, objective, and scope of study. Then the literature review, types of membrane, surface modification, metal oxide nanoparticle, and methodology, membrane fabrication and characterization of kaolin modified membrane. Expected result for the surface morphology, pore size, functional groups, performance, and hydrophilicity. And the conclusion is about future advantage of kaolin modified PSF membrane. For the introduction, first is research background. My project is involving the membrane separation technology. Membrane separation technology is said to be the most cost-effective method to remove the oil from oily wastewater. As currently, our world needs clean water resource, so membrane separation method is beneficial for the wastewater treatment. There are three types of membrane processes, which are microfiltration, ultrafiltration, and nanofiltration. All three processes has different membrane pore size, which will affect the efficiency of the wastewater separation. Nanofiltration has narrowest pore size compared to microfiltration and ultrafiltration. Microfiltration membrane use the pore structure to separate the contaminants, oil and water from oily wastewater based on size exclusion. Then, there are two types of membrane, which are polymeric and ceramic membranes. Polymeric membrane become the first choice for the membrane separation industry. This is because it is easy to control the membrane pore size during the membrane formation. Example for polymeric membrane is polysulfone, polycarbonate, polypropylene, and other. Polymeric membrane is inexpensive compared to ceramic, which become one of the reasons on why it being used in this project. One of the example of polymeric membrane is polysulfone. It has been widely used in wastewater treatment as it have high mechanical strength, stability, and ease of modification. But it also has disadvantage, which the hydrophobicity will result in membrane falling. That is why the polysulfone membrane need to be fabricated through nanoparticle surface coating. For fabricating the membrane through surface coating, it need a linker such as uptase, polyasparmine, or trimesoyl chloride. In this study, trimesoyl chloride will be used as it can reduce the biofouling. Metal oxide nanoparticle is applied as the coated layer as it will forming a hydrophilic network when being coated onto the membrane surface. The example of metal oxide are alumina, silica, and other, but they are expensive. Kaolin nanoparticles are also one of the metal oxide, but it is a clay base. Kaolin nanoparticles have inexpensive price, so that it can replace the other metal oxide to be used in this project. In this study, the thing that we will be observed is the effectiveness of kaolin modified polysulfone membrane for oily wastewater purification. For the problem statement, there are three main points. The first one is the major concern in polymeric membrane technology, which is the membrane fouling. Fouling will reduce the permeability and efficiency of the membrane. Fouling can be caused by the pore blockage. The second one is polymeric membrane, which still having low adhesion even after the fabrication of nanoparticle onto the hydrophobic membrane are made. This is because the common linker like uptase and polyasparmine are not chemically bond. And the last one is the difficulty on achieving the robust layer on a membrane. In order to overcome it, a uses of trimesoyl chloride will have highly potential as robust linker. For the objective, there are three of them. The first one is to fabricate kaolin modified polysulfone microfiltration membrane via chemical modification with trimesoyl chloride. The second one is to characterize the physical and chemical properties of kaolin modified polysulfone microfiltration membrane. And the third one is to test the performance of the modified microfiltration membrane for the treatment of oily wastewater. Scope of study. The first one is the morphology and distribution of kaolin nanoparticle by varying kaolin loading from 0.05 to 1.0 weight percentage on polysulfone microporous membrane. It expected that an increase of kaolin loading will reduce the porosity and pore size of the membrane. The second one is the characterization of the physical properties such as morphology, pore size, porosity, chemical bonding, and other, using different devices such as the Fourier transform infrared spectroscopy, X-ray diffraction, and other devices. The third one is testing the microfiltration membrane using dead-end filtration with synthetic oily wastewater. Water quality tests using UV visible adsorption will be made. Then the water quality will be compared between the modified polysulfone membrane and the pristine membrane. Then for the literature review. The first one is about polymeric and ceramic membrane. It is said that the polymeric membrane is very economic and simple to adjust the pore size during membrane formation. The example of it is polycarbonate, polypropylene, polysulfone, and polyethylene. All four is within the artificial polymers, which beneficial to the fabricating process. They are widely used within the microfiltration and ultrafiltration processes. But they also have disadvantage, which is their hydrophobic nature, which become the limitation for the aspiration performance. This is why there are several developments which focusing on improving the membrane weakness. Meanwhile, for ceramic membrane, it is synthesized using inorganic materials such as alumina, silicon, titanium, or zirconium oxide. It consists of three-layer structure, which are the support layer, transition layer, and function layer in a sandwich-like structure. Ceramic membrane also has high thermal stability. The disadvantage of ceramic membrane is it exhibits high flux and expensive. There are three surface modification methods, which are surface coating, blending, and grafting. Firstly, surface coating is the common membrane modification methods which improve the anti-fouling properties. This method is the simplest and cheap method compared to the other. The method is done by covering the membrane surface by the coated layer. When the membrane is coated, then it will have a good stability for a long time without being wet. The example of the linker for the coated layer is trimesoyl chloride and uptase. The uses of trimesoyl chloride within the surface coating will help in reducing the biofouling. Next is the blending method. This method involves the mixture of two or more polymers. Blending modification is usually done before the membrane formation, which hydrophilic component is added into the membrane casting solution. Blending method will improve the crucial surface properties. And the last one is grafting method, which is popular for the organic and inorganic substrate. Surface modification. Grafting is done when macromolecules are attached to the substrate surface. There are two grafting approaches, which are grafting to and grafting from. Then, for metal oxide nanoparticles, it is also known as inorganic nanoparticles. It is widely used in membrane fabrication because of the good synthetic and physical properties. There are also several studies which mention that metal oxide nanoparticles help in surface roughness modification and also increase the active site on the membrane surface. Every metal oxide nanoparticle consists of polar functional groups such as hydroxyl, sulfonic, amino and carboxyl group. The polar functional group will increase the adsorption process of water and also the hydrophilicity of the membrane. The example of metal oxide nanoparticles are silicon and kaolin nanoparticles. Kaolin nanoparticles are hydrophilic and readily disperse in water. Kaolin nanoparticles are inexpensive compared to another metal oxide nanoparticle. When being coated on the membrane, it will produce super-hydrophilic surface, which beneficial for separating oil and water droplets within the wastewater. Then, for the methodology, I will explain about the membrane fabrication. There are three main steps, which are alkaline treatment, trimesoyl chloride treatment, and kaolin coating. The first one, we will treat the polysulfone membrane substrate using sodium hydroxide aqueous solution with concentration 7.5 mol per liter. The condition is 70 degrees Celsius for 3 hours. Then, take out membrane, wash with molecular water. For the trimesoyl chloride treatment, immerse the membrane in 0.5 weight percentage of trimesoyl chloride heptane solution. The condition is 25 degrees Celsius for 30 minutes. And the last one is the kaolin coating. First, immerse the trimesoyl chloride treated membrane in kaolin aqueous solution with different kaolin loading, which are 0.05 to 1.00 weight percent for 30 minutes. Then, wash again using molecular water and dry the modified membrane. Then, for the characterization of kaolin modified membrane, there are several devices that being used for characterize the kaolin modified membrane. For the first one is mercury intrusion porosimeter. It is used to measure the membrane pore size using non-wetting liquid penetration. Then the second one is scanning electron microscope (SEM) to identify the membrane morphology, chemical composition, and crystalline structure. The third one is the tensile test. It is to test the mechanical strength of the fabricated membrane using the tensile testing machine. The fourth one is the rejection performance test to evaluate the membrane's anti-fouling properties using the spectrophotometer. The fifth one is the water permeability test. It is to investigate the permeation properties of the modified membrane. Then we will also use the gravimetric method, which is to measure the porosity of the modified polysulfone membrane. We also use the X-ray diffraction to determine the crystallographic structure of the membrane materials. And the last one is the Fourier transform infrared spectroscopy to observe the component on the fabricated membrane surface and the chemical structure and functional group. We will proceed to the expected result. Expected result is based on the surface morphology, pore size, functional groups, hydrophilicity, and performance. For the surface morphology, modified polysulfone membrane is expected to have better surface morphology than the pristine one, and the pore size is decreased compared to the pristine polysulfone membrane. The membrane also expected to have more functional groups present on the membrane surface. It makes the peak intensity of the functional group increase proportionally to coating concentration. It also will produce hydrophilic membrane surface through surface coating. It then leads to less susceptible to fouling and lessening the flux. Separation performance toward oil in water emulsion improve. Water permeation rate is increased and the rejection performance also improving. Lastly, for the conclusion, the modification of a hydrophobic polysulfone (PSF) membrane to a super-hydrophilic and oleophobic membrane in water is highly advantageous to solve the issue related to fouling and membrane performance. It is also expected that a promising modified membrane with a lower cost and a more robust interface will be produced in the future. The goal of this research is to make the treatment of synthetic oily wastewater easier and more efficient, as the kaolin-modified polysulfone membrane is both cost-effective and time-efficient. And here I provide the Gantt chart that I do for the final year project planning over the week. That's all. Thank you for listening.